In last lecture we have seen the alpha decay and beta decay. We have seen that this alpha decay was completely explained with the help of a Gamo's theory of alpha decay, in which Gamo's used the quantum tunneling effect to explain the alpha decay, and beta decay was explained with the help of a neutrino hypothesis, and Fermi gave the Fermi golden selection rule to explain the beta decay. Now in this lecture we are going to see what is this gamma decay. Now in a alpha decay and beta decay we have seen that the nuclei are changing to the another nuclei. For example, so this is a example of alpha decay. So this nucleus is changing to some another a minus 4 plus this 2he4. So this x is changing to y. Similarly, if you are dealing with a beta decay, then in this example also this nucleus is changing to the another nucleus. So with this electron plus electron neutrino, like this, so, or the anti-neutrino. So in alpha decay and beta decay, so the nucleus is changing to the another nucleus, but in a case of a gamma decay, nucleus is not changing, it is only just de-exciting to some lower excited states or to some ground state. Suppose this is the excited state of the nucleus, then it is de-exciting to some another excited state or some ground state, and whatever, this is also excited state. So if there is any nucleus which is having some extra amount of or the surplus amount of energy than the ground state, so it may give out some gamma decays, and it will attain the more stable state by giving out some sort of energy, which we call it as a gamma rays. So these gamma rays are nothing but the electromagnetic radiations. Here also in a gamma decay, the nucleus in excited states give out some gamma radiations and it attains some more stable states. So this is called as a gamma decay. So these electromagnetic radiations, they are in a form of a photons, and these electromagnetic radiations can be classified into two types as electric and electromagnetic radiations. So now we know that the electromagnetic radiations are coming from the oscillating charges. So oscillating charges is the origin for the electromagnetic radiations. We know that in the nucleus, which are having protons and neutrons are arranged, and which are the charged particles. We know that in a quantum mechanics, neutron and protons are having charges. Neutron is also having charge, that we have already seen. Proton is made up of UU and D corp, whereas a neutron is made up of DD and U corp. Now we know that in a nucleus, if the charge distribution is symmetric, like this, if this is a nucleus and a charge distribution is symmetric all over this nuclear volume, so this is a symmetric nucleus where the charges are distributed symmetrically all over, and the electromagnetic radiations or the potential created by such a type of a symmetric nucleus is radially equal in all directions. Potential created by such a type of a nucleus is same in all directions. Or electromagnetic radiations which are given out by such a kind of a symmetric nuclei are isotropic in all directions. From the nuclear shell model, we have seen that the charge distribution of the nucleons inside the nucleus is not symmetric, so it will have some dipole moment. For such a type of a case, it is called as a nuclear charge distribution may have some dipole moment, and which is called as a, it may have the charge distribution which is not symmetric. Okay, it may have the charge distribution more in some area and less in some remaining area. So such a kind of a nucleus can have the potential which is having a dipole moment, or there may be, so I could call it as a dipole. So there could be a nucleus which is having quadrupole charge distribution or octapole charge distribution. So the electromagnetic radiations which are given out by the symmetric or by dipole or quadrupole or octapole charge distribution are different, and by measuring those we can say whether the electromagnetic radiation is coming from this dipole distribution type of a nucleus or quadrupole type of a charge distribution nucleus, and so on. When this dipole or a quadrupole or octapole charge distribution, these are oscillating, or they are forming some current loops, the magnetic field will be associated with that. So the magnetic field associated with the dipole moment, so that is called as a M1. The dipole which is a magnetic dipole which is associated with the quadrupole, so it is called as a M2, and with octapole it is called as a M3. Electric radiations which are related to the dipole moment, they are called as a E1. With the quadrupole they are called as a E2 and E3 and so on. So the electric and magnetic radiations which are generated due to the dipole charge distribution and its oscillations are called as a E1 and M1. The E2 and M2 are the electric and magnetic radiations which are generated due to the quadrupole charge distribution, and E3 and M3 are the octapole charge distribution electric and magnetic radiations. So the selection rule for angular momentum can be written as, so this ji is the angular momentum of the initial state, so it is given by jf plus this l. So this l is the angular momentum of the gamma radiation. I can write that this ji plus jf, so it is less than equal to this l less than equal to ji minus jf. So along with the selection rule of the angular momentum, there is also a selection rule for the parity. So this pi is the parity of the initial state, and pi f is the parity of the final state. So this is the selection rule for the electric radiation, and the pi I is equal to pi f into minus L raised to L plus 1 is the selection rule for the magnetic radiations. So we can take one example for this. Suppose there is any nucleus, say it is having the ground state as a spin parity as a 0 plus, and excited state spin parity as a 2 plus. Nucleus is trying to de-excite from this 2 plus to the 0 plus. Say this is a even nuclei. So the ground state spin parity is a 0. Suppose this is a even nuclei, and which is trying to de-excite from the 2 plus to the 0 plus. So let us see whether it is possible or whether the electric or the magnetic radiations are possible for this. Now we know the angular momentum selection rule, that this ji is equal to jf plus l. Let me write this: ji plus jf less than equal to L less than equal to ji minus jf. So ji plus jf is equal to 2 less than equal to L less than equal to, so ji minus jf, so that is also again 2, so L is equal to 2. So if this L is equal to 2, so let us see what is the parity. Parity is not changing over here. Here also parity is positive. Here also parity is positive. So if I take this pi I is equal to pi f minus 1 raised to 2. So the pi I is equal to pi f. So the parity selection rule is also valid and the angular momentum selection rule is also valid. Therefore, there is a possibility, or uh, E nuclei is de-exciting from the 2 plus to 0 plus, but the magnetic radiation is not possible. And when this L is equal to 2, then I will call it as a E2, and it is coming from the quadrupole charge distribution. Okay, this is how, by measuring the angular momentum of the outcoming gamma radiations, we can calculate where the gamma radiation is coming. By measuring the angular momentum of the outcoming gamma radiation, we can calculate from which excited state the nucleus is de-exciting to the which state. So here if we measure the angular momentum of this outcoming gamma ray, which is L is equal to 2, from this and from these calculations we can say that the gamma ray is coming from the de-excitation of the nucleus from the 2 plus state to the 0 plus state. Now see here, let us see whether it is possible. So this 0 plus to 0 plus, whether it is possible for this particular nuclei. So we can say that this Ji plus Jf, so it is 0, and this Ji plus minus Jf, that is also equal to 0. So L is equal to 0. So if this L is equal to 0, pi I is equal to pi, this is not valid, so electric radiations are not possible. Similarly, if pi f is equal to minus 1 raised to 0, therefore that in that case also pi I is not equal to pi f. Okay, so we can say that the electric and magnetic radiations both are not possible for 0 de-excitation of this 0 plus to the 0 plus ground state. In these cases, sometimes there is a possibility of internal conversion. So this much amount of energy, we know that in a quantum mechanics, the nucleus is a quantum mechanical entity, and for the most of the time, so this 2s electron wave function is present inside the nucleus. So we can say that this electron may absorb this much amount of energy and it may go to the excited state, and electron may come out of this reaction, and such a type of reactions are called as a internal conversion reactions. So the gamma radiation is not coming out of that and the electron is coming out of that, and this type of a reaction is called as an internal conversion reaction. So the moral of the story of the gamma decay is the nucleus is not changing to the another nucleus, but it is just de-excited from higher excited state to the lower excited states or the ground states. And there are some selection rules for the electric and magnetic angular momentum as well as the parity, and by measuring the angular momentum and parity of the outcoming gamma radiation, we can calculate from where the gamma radiation is coming from. And there is also probability of the internal conversion, in which the electron may also absorb the available amount of energy and it may also get to the excited states.